we're going to wrap up this half-life stuff now. Okay, so hopefully you came up with a graph that looked somewhat similar to this for your decay on your half-life stuff for your pennies. And so what we see is this exponential decay for substances as they're going through half-life. We can literally at any 2 points along there find two numbers that are half of each other. So if I had, let's say I had, here was 60 and here was 30, you could actually kind of like come down, and I'm sure that's not a straight line, but it's supposed to be, and you could come up with your half-life. So we would say T1 half, that means half-life time. So we could like from our graph figure out a half-life from it. So we could do 60 and 30, 50 and 25, 150, whatever. And we should be able to look at our graph and be able to get a half-life. So I kind of mentioned before some half-lives. So I looked up some half-lives, and this is what I got. Carbon 14, which we'll talk about here in a little bit, 5,730. Here's one in days. This got smeared. This is microseconds. So that's quite a lot smaller than milliseconds. And then the one we've heard of before about uranium, we're talking almost 5 times 10 to the 9th years. So very fast, very slow, anywhere in between. Okay, so we're going to go through two different ways to calculate half-lives. And honestly, I just kind of logic my way through most problems. You're going to get assigned some problems to do that with, and you can logic your way through those as well. So kind of when I logic my way through, I think about how many half-lives have passed or what's going on in terms of a half-life. So if I started with a sample of a substance that was 2 grams, after one half-life, I would have half of it. So I would have 1 gram after one half-life. And when we had 2 half-lives pass, I should have half of this, so I should have 0.5. One more half-life, I should have half of this number, so that would be 0.25, so on and so forth. So you can kind of logic my way through those. If I know a substance has gone through 3 half-lives, and at the end of 3 half-lives there were, say, 5 grams, and it's been 3 half-lives, that's half of whatever it would have been at 2, so that would have been 10. This is half of whatever that would have been, so that would have been 20. And this is half of what the initial amount would have been, so that would have been 40 grams. So you can kind of logic your way through the problems. There's also a math equation, if you like that better. So N is equal to N0 times 1/2 to the power of N. So this N here is the amount remaining. N0 was how much you started with, so your original amount. And here the little n is the number of half-lives that you've gone through. So depending on what they ask you in a problem, you can have your unknown wherever and solve. I'm going to work through a couple of problems. I'm going to show you the logic way. If you would prefer to put it into the equation and solve, you can do that as well, whichever way you want to do it. So I'm going to go back to my way. You've got the equation. You can use it too. So a couple of different problems that I've got, practice problems here, is that I have a 10-gram sample. And I want to know how much after 4 half-lives. So that's the question. How much is remaining after 4 half-lives? So my 10 is my starting amount. So after 1 half-life, I'm going to have half. After 2, I'm going to have half of this number, so 2.5. After 3, I'm going to have half of this, so 1.25. And after 4 half-lives, I'm going to have half of this number, so I don't have enough light on my calculator. Half of 1.25, that'll be your answer. So it would be 0.625, maybe, I think. So that's kind of my process of kind of going through this. I have one more set up just a little differently. Sorry, the dogs are playing. The other one says, that mercury 95, or sorry, 195, has a half-life of 31 hours. If 5 grams are there initially, how much is present after 93 hours? All right, well, first I've got to figure out how many half-lives is that. 1 half-life is 31 hours. So 93 hours, how many half-lives have passed? 93 divided by 31. So I know there has to have been 3 half-lives that have passed. So I'm starting with 5 grams. So I just logic my way through it. 1 half-life, 2.50, 2, and then 3 half-lives. And so then you will get your answer after 3 half-lives. So you can kind of follow the logic way. It works on the problems I'm assigning you. It probably won't work on all of your college problems. If you do these, you will have to, for some of those, go ahead and use the equation. But my way works for what we're doing. So whichever way you like, and you'll have a few of those to do. Last thing. Has to do with radiocarbon dating, and I forgot to make my little slide. So, carbon dating. So, for carbon-containing compounds, we might want to try to find out how old it is. So, you find a random bone, and you want to know how old that bone is. We will sometimes use carbon dating to try to figure out the age of compounds if they contain carbon. So here's the deal. I have a little problem with it, and that's probably the bad science teacher thing to do because it's built on an assumption. Carbon-14 is the radioactive carbon that is used in carbon dating. So the basis of the entire food chain is based off of carbon. Not a problem with that. So plants take in carbon. they will take in some carbon-12 and some carbon-14. They incorporate that into their bodies. We eat the plants, the animals, that carbon just keep passing through the food chain. No problem. So a small percentage of that carbon is carbon-14. The vast majority of it is carbon-12. This has a predictable half-life. It goes through a predictable decay. It is carbon, let's do it like this, 14,6 beta. And so this would be 14, that would be 7, and nitrogen. So carbon-14 decays into nitrogen, and it gives off beta. If we can come up with the amount of beta that's being given off, we can kind of use that, like our half-life calculations, to work back to how many half-lives have passed in a substance. So the half-life was 5,730. So this is like super accurate in the 7,000 year-ish range, and reasonably accurate up to about 30,000 years. So that's at about, I don't know, a little less than 6 half-lives. It's reasonably accurate. After that, it kind of gets off. Remember when you were flipping your coins or flipping your M&Ms? Sometimes people kind of get hung and they have one and they flip it and they have one and they flip it and they have one, and it just keep kind of hanging on. So when you get to a certain number of half-lives, it's not very accurate anymore. So it's reasonably accurate at 30,000 years old. After that, it's not going to be accurate. So if we can measure this, we can figure out how many half-lives have passed. So 2 half-lives have passed. Oh, well, we can estimate the age at 11,000 whatever years. 3 half-lives have passed. Oh, we can estimate the age. That makes sense. Here's the problem. It's based on an assumption. And that's the part that I've never had adequately explained to me is, why do we assume that? Because I've always been taught we don't make assumptions about stuff. Carbon-14 is formed naturally when cosmic rays hit the atmosphere. So it's being formed. The assumption is that it's always been formed at the same rate. Maybe scientists have a really good line of evidence for why they think it's always been formed at the same rate. I just don't know what that is. It's never been adequately explained to me. If carbon-14 has always been formed at the same rate, then carbon dating, golden, it's good, no problem. But if that rate of carbon-14 formation was faster or was slower, throws off our whole dating process. So if we went through a period where carbon-14 was formed really, really, really fast, there would be a lot more carbon-14 in the atmosphere. Things would have more carbon-14 in them, and it would mess up our dating process, because our dating process is based on the idea that carbon-14 has been formed at a continuous rate forever. And like I said, you can look that up and you can find some great evidence on why scientists say that that's the case. Share it with me. I would love to know that. But if that carbon-14 hasn't been formed at the same rate, then we're going to have mess up in our stuff. And if it was formed faster or formed slower, that's going to make our dates be off. Either say that things are way older than they really are, or they're way more recent than they really are. So anywho, that's kind of the idea of carbon dating, and we use our half-lives to kind of work through that. You're going to have some practice on some half-lives, and like I said, you can logic your way through them, or you can go back and you can use the math problem.